We're gonna start recording. Hi everyone. Good morning, good afternoon, good evening from everywhere in the world. Welcome back to phase 2 of McMedHacks 2023 and the week 5 of the workshop. Today we have our speaker, Dr. Roy Key, to give us a seminar. I'll just start right now on the little housekeeping stuff that we usually do at the beginning. Here we go. Yeah, I can have the Discord open. If the mentors are here, feel free to turn on your camera and I will introduce you as usual. 1 second. Yeah, Roy, if you can, since you're a co-host, you can feel free to let people in as well. And yeah, as I mentioned, today we have Dr. Roy Keys as a speaker. Again, if you have questions, feel free to shoot a message on Discord. I'm also answering there as well. Since we finished phase 1, we had some questions regarding certificates and so on. So all the phase 1 and phase 2 certificates will be released at the end of the workshop series. And how it works is that if you have attended a session live and you have attended that session for more than 30 minutes, we'll have a record on Zoom and we can see that. So if you have attended more than 70% of all of the live sessions, including the seminars and the workshops on the weekends, you will get a certificate. In events where you couldn't make it live, we have provided quizzes that you can fill to make up for that attendance that will contribute to the 70% as well. We have all the contents on Gumroad as well as the Google Drive folder link. They're the same thing. If you can't really access one, you can go to the other. So as I mentioned, we have finished the first half of this summer school. Last week, we have gotten to the point of transfer learning in medical imaging, and starting in phase 2 today, we're going more into the state-of-the-art of the methodologies and practical uses in medical AI these days. And this week, we're starting with self-supervision workshop tomorrow. Today, and you can go on our website to take a look at the program for this week. So I'll just briefly introduce 2 of our mentors this week. If you're here, feel free to say hi and answer any questions in the chat. But we'll have a tutorial with them this coming week during the time when they're available. We have Ivaksi and Deganta. And Ivaksi is currently a PhD student at Mila and in Montreal, which is the Montreal Institute of Learning Algorithms and ETS, pursuing research on explainable and generalizable machine learning. Her research application is mainly computer vision and medical imaging. In the domain of medical imaging, she's led and published projects on the topic of medical image segmentation, interpretability, and generalization in histopathology images and dermatology images. He's interested in real-world applications and also has gained industrial experiences being a research intern in Magia. She's also obtained a master's in engineering from Imperial College London. Our second mentor this week, Deganta, is a graduate student at UDM, also from Mila, majoring in computer science, specializing in machine learning. His primary academic research include, but not limited to, theoretical deep learning, sparsity, multimodality, and online learning. And in the past, he's worked on segmentation problems in hospitals in India, and so on and so forth. So thank you so much for joining us this year. We look forward to your mentorship and tutorials for our participants. So I'll briefly introduce our speaker today, Dr. Roy Keys, who has also been a speaker in 2021, which is the first year that we have started in McMedHacks. His title of his talk today will be on natural language processing, buy versus build in post-ChatGPT world. Roy, this is a description of you that I found online. If this is not accurate, feel free to correct me. So Roy has worked in data science since 2012, building and leading teams at multiple tech startups, as well as consulting for clients across a wide range of industries. Prior to data science, he's received a PhD in computational physics, focusing on medical applications. He has also published books on deep learning. A recent one includes Seth's Guide to Deep Learning, Hiring Data Scientists and Machine Learning Engineers, a practical guide. So, and he's also a very good friend of my PhD supervisor, Dr. Anger. So thank you, Roy, for accepting our invitation today. Please go ahead and start your talk. We look forward to it very much. Thank you.
All right, let me see if I can share my screen and get to where we want to be. Okay, I'm going to try to do a slideshow. All right, I think that's working. Does that look? Eugene, can you nod if that's working? If you can see my
Yeah, it
screen.
works.
Okay, great. So let me jump into this. So today I'm going to talk about there's a standard question in industry that's build versus buy, and I'm going to specifically talk about natural language processing and the sudden emergence of these models like ChatGPT and what that means for people who are doing natural language processing. So the outline, basically, first well, Eugene did a good intro. I'll just run through that really fast of who I am, and then talk a little bit about natural language processing. I know some of you will know what that is. Some of you that's going to be a relatively new thing. And then we'll talk about large language models, which the same applies. Some of you probably are familiar with those. Certainly, I would assume almost all of you have seen something about ChatGPT, talk a little bit about what those are. And then finally, talk about sort of the implications for doing this stuff in 2023. So as Eugene said, my background is actually in medical physics. That's how I kind of ended up talking to you today. I have basically I did radiation simulation. So there's a lot of medical physicists I know that are in this audience. And after I finished my PhD, I went to work in a cancer clinic for a little while. I did a very unusual experiment at CERN, and if anyone wants to ask me about that later, we can talk about that. I then switched to data science back in 2012 after I had been working in a clinic, and basically since then I've been working at tech startups or consulting with tech startups, and my focus is kind of on building and leading data science teams and machine learning, building machine learning powered products. So I've just by kind of coincidence been at this intersection of medical physics and imaging and radiation therapy, and then data science and machine learning. I have written some books that Eugene mentioned. The most recent one I wrote is called Seth's Guide to Deep Learning. That's like a short overview of like all the concepts in deep learning. Before that, I wrote a book called Hiring Data Scientists, Machine Learning Engineers. So I've spent a lot of time on hiring and things like that for the industry. And recently I have what seems to be kind of a popular blog post that's about embeddings. So at some point, I'm sure during this summer course, you'll be talking a lot about embeddings, and you can find that at my website, roycoding.com, if you want to read what might be the shortest definition of embeddings. It's a important and tricky concept. So I'm going to start by talking about natural language processing. At its core, natural language processing is basically just how can we get computers to understand and deal with human language. Mostly these days it's around text, but also it can be audio language. But I'm going to start off with some examples of things that fall into this category. So one that's popular if you're doing sort of especially intro machine learning type things, people like to use an example is sentiment analysis. So for example, if you're looking at product reviews or something, or service reviews, is this a negative review? Is it a neutral review? Is it positive, or comments or something like that? How can you take that text and just automatically classify it as with a sentiment? Named entity recognition. This is also, there are various names for this, but basically this is trying to look into text and extract the important known entities or things. So obviously, oftentimes that's something like, finding people's names, finding companies, finding dates, important things like that. Look here, look, we have locations, organizations, person. How can you do that automatically? Topic classification is another one. You might look at documents, articles, whatever, and you want to know, what is this about? And you may want to take a big giant stack of text documents and put them into different piles via topic classification. So as you can imagine, there's lots of text in there, and there may be multiple things that are being discussed, but what are the central themes? Central or single central theme, or multiple central themes? That could be a single label or multi-label classification. Machine translation, this is one that's really picked up, I'd say, in the last 5-ish years. These are all translations I did using Google Translate, and actually a couple of years ago. This is an old slide that I'm recycling. So if any of these look bad, blame Google, don't blame me. But this is one of the most useful types of natural language processing tasks is machine translation. How can we go from one language to another, back and forth? And obviously there are many, many uses for this. Text summarization. These are all closely related if you start thinking about them, but text summarization is how do you take any long bits of text and try to pull out the central things into something small. And as you can imagine, if you as a human need to look at lots and lots of documents that are long, that getting summaries is nice. And as you can also imagine, this is an interesting problem. You have to digest the meaning of what's in there and then try to restate it in a different form. And then finally, voice recognition, transcription. This is something that also, I would say, has really become prominent in the last, say, 10 years, whether it's talking to things like Apple Siri or Amazon's Alexa, or using your phone to transcribe speech. This is a kind of task that's been around for decades, but with recent advances in machine learning has gotten much, much, much better. So all that said, I think there's a question about, how do you do any of these things? How do you do it? And this talk is about operating in a post ChatGPT world. So the starting point is, what were we doing right before ChatGPT and all of these models came out? And so that's why this slide says, how do you do NLP in 2022? And a ton of things have happened in the years preceding 2022. So just a few years before this, I gave a different talk that was kind of like, what are we doing in NLP now? And so things were very different, but the rapid pace of change means that we're just thinking about the olden days back in 2022 now, even though we're only halfway through 2023. And the key really to how you would do most NLP in 2022 was taking pre-trained neural networks plus transfer learning, which I guess is the unit you're working on now. So that's good. You've seen some idea about transfer learning, and that can apply. It was really, I would say, really took off with images, but now it's also the dominant way that you handle natural language processing tasks. And this was really, really kicked off by the advent of the transformer. That was a new kind of neural network architecture that was first published in 2016 by researchers at Google. And a few years later, there had been enough developments, especially in the open source world, that there were lots of practical versions of this network, and to the point where it began to dominate natural language processing and was spreading into computer vision. As you may, I'm not sure if you'll cover that or not in this course. But basically, these are models that are able to use very large amounts of text to learn from, and we'll talk about a little bit more about that in a second. But basically, using these models that have been trained on tons and tons of text using self-supervised learning, which we're also talking about, and they become very powerful. And one thing they can do is they can produce very rich context-aware embeddings, which is embeddings I mentioned before. If you haven't, and I can answer any questions at the end if you want to talk more about that. And then because these are language models, they can generate text. And then finally, the most importantly, they can be adapted to many different tasks by fine-tuning via transfer learning. So I'll talk a little bit more about this, since it's kind of a central concept, and it's playing a big role in both 2022 and 2023. Transformers are basically an encoder decoder language model, which means there are two main parts. The first part would take in a sequence of text, and the second part would produce a sequence of text. So this is you can imagine that if you're doing something like machine translation, that this is obviously a sequence to sequence kind of task, where you're taking in one sentence or whatever and outputting another one. And in this case, that first chunk is taking that input, it's doing something, which is the encoder, and basically producing a rich representation of that input in this quote low dimensional embedding space. Basically, you're taking something and you're trying to put it into a way that will have more meaning for the task that you're doing. And then the decoder is taking that encoded input, and then it is building up a new output sequence. And basically, this is one of the big differences, that inside these blocks, it's using a new type of network that's called self-attention. There's a lot more to it than just that, but that's kind of where I'll leave it. But the important thing to note is that the self-attention network is not a convolutional network, and it's also not a recurrent neural network, which is the main way of doing this type of task in the past. And it's very efficient. All right. Another interesting thing is that the transformer has these two main parts, which is the encoder and the decoder, but you can actually break those apart, and you can use those two different pieces for different things. So one of the famous models that tons of other things are built on, that's based on transformers, is BERT, which is I forget what it stands for. It's something like bidirectional embedding representations with transformers, something like that. Basically, the BERT is an encoder, and it's trained to take in some sort of text input and then produce a very useful embedding at the end. And then on the other side, you can also build models with just the decoder. So GPT type models, including ChatGPT, are based on the decoder side. So instead of also training the encoder, they just take the input directly, and then they rely on the power of the decoder block, which is almost identical to the encoder, but slightly different. They rely on that to create a rich representation on the way to generating output sequences. So on the practical end of things, in 2022, how you do NLP, like I said before, the headline is taking pre-trained neural networks and then applying transfer learning. And what you would do is basically you'll go to a place like Hugging Face, for example, and get pre-trained open source models that are based on transformers. And then you will use your task specific data to fine tune the model to whatever your use case is. So for example, if you wanted to do, let's say, sentence classification, is this sentence a question? Is this sentence a statement? Is this sentence anything you can imagine? Or you could also use, say, sentiment classification. What you would do is you would pass it through, you would take a BERT-based model or similar, and then what you would do is you would either add another layer or change the final layer and basically fine tune that to what you were doing. So you might say, here are some input sentences, here are some labels that I want to put on those, pass those sentences through your BERT-based encoder model, and then basically you're just training that final layer to make some classification. You could fine tune everything if you wanted to, but in general, you're just going to touch the last layers, partly because the models are big enough that if you are trying to change all the weights, it may take longer, or you need more data or more hardware than you might want. Okay, so now I'm going to switch to talking about large language models. There are some pedantic points you could make there, like, BERT, maybe that's already a large language model, but suddenly the way that people are talking about large language models are about things like ChatGPT and these very big models. So the reason I'm giving this talk is because back in November, December or something, it was like one day suddenly everything was about ChatGPT. If you were paying close attention in the sort of machine learning world, this kind of hit, and then a few weeks later, the press picked it up, and suddenly it was just everywhere. ChatGPT is just the latest thing that was released by OpenAI. That's a large language model. They had a series of GPT models coming up to this, but because of the way that they had fine-tuned ChatGPT to work as basically a chat bot, it really, really caught the attention of not only the machine learning world, but the wider public. And, in theory, it is the fastest ever product to get to 100 million users worldwide in just a few weeks. But if you are in the machine learning world, like I am, and you also would suddenly get people start asking you about this. What's going on? What's the deal with ChatGPT? What can we do with it? What's our AI strategy? Suddenly became a question that every CEO is asking their company. So what are LLMs? Ultimately, they're just language models with lots of parameters. And typically they're trained on lots of data. One of the big differences between some of the stuff that's been done in the past and kind of filtered down is that these big, powerful models are still big enough that the amount of hardware you need and just the money you need to really train these from scratch is it's out of reach for not only most individuals, but many organizations. They can't do this. You hear some of the numbers that come out of places like Google or OpenAI or some of the other big companies, and they're potentially spending millions of dollars to do some of these training runs. So not the kind of thing that you can necessarily do at home. That said, there's been a history with a lot of these large models that eventually some of the things that were thought to be crucial at the beginning, people have been able to take some of those out, perform some kind of tricks and hacks, and make it so that you could train some of these on much lower resources. The key thing about language models is they can generate text. So these big language models, they're able to do that in a way that's typically indistinguishable from text a human would write. Whether or not that's what they're saying is true is a different question, but I think for the most part, these models have gotten strong enough that most people would say, yes, they're producing language that looks like language a human would produce. Key to this discussion is that they are also able to perform zero-shot tasks extremely well. We'll talk about that in just a second, but that's one of the key points. Also, because they've been trained typically on so much data that's general data from across the internet, they seem to know a lot. And then also you've probably seen some examples where they seem to think they know more than they actually do. And there are a lot of reasons why they do that. The main thing is that their goal is to produce output. And so if they're not trained in a way that would make them stop before they just put an output, they will try to answer any question you give them. Okay, I'm going to come back to zero shot. So zero shot is basically when a model is given a task that it has not been specifically trained to do. So for example, that might mean if you had a model that has been designed to answer questions, and you ask it instead to produce some computer code, or a computer code in a language that it doesn't know, and it's able to do that at some way, well, that would be a zero-shot task. That's a bad example, but zero-shot essentially means something that it hasn't been specifically optimized to do. How well can it do that? Language models really do one thing, and that is they predict the next token in a sequence. Most of the time in this discussion, we're talking about the next word in a sentence or something, but a token in a sequence could also be anything. You can use these same architectures to do stuff that's genome stuff, or audio, or images, if you set the images up as sequences. But basically, given some sort of input sequence, which we'll start talking about also as prompts, language model will then try to give you what comes next. And it turns out that if you also give in a prompt, you put in input output pairs that you might expect the way we'd normally do supervised learning. If you just put some of those in there, these large language models can often predict what you would expect. So the model itself may be trained just to generate language. It just says, here, the cat sat on the, and then, what's the next word? It could be the mat, the dog, the existentialism. It's going to rate what are the words that are most likely to come. But if you also give it, instead of just a short sentence like that, if you say, here is a review, and the label on the review is negative. Here's a review, and the label is positive, and you give it several of those, and then you say, what is the label on this review? And because of the zero-shot capability, these types of models are able to do pretty well in that they might add the correct label to that, because they can start to pick up the pattern. Now, at the end of the day, all they're doing is just adding the text that's supposed to come next, in that they're predicting is the most likely. But because you can put these types of examples and things in the prompt to give it this context, it's very good at doing this. This is also a buzzword term there. It's called in-context learning. So what this really means is, and this is the same as zero-shot task, is that you're not changing any of the weights in the model. You're just giving it an input that when it does the output, it's able to answer what you're doing. So the learning is ephemeral. If you went back and just asked the model, what's the sentiment of this sentence, it might not be able to do it nearly as well. But if you put in this prompt context, you put these examples and things, it may be able to give you what you want. And more specifically, you'll see things also like, here is some data, please, or I'm going to give you some data, reformat it using this JSON sequence, a JSON template that looks like this. And then you can ask it, and potentially then it will break things down and put it in a JSON template that you want. There's a lot of pitfalls to that, but it is a thing you can do. And so obviously, because you're not changing any of the weights of the model, if you then don't tell it to do that and you just say, give me this in JSON, it will then just make up another format versus maybe trying to do what you'd specify. We'll talk a little bit more about that later. So given that there are these new models that are super powerful, they're very good at zero-shot learning, then this new question comes up. How do you do these kind of NLP tasks that we mentioned in the beginning in 2023? Should we still be thinking about the way you did it in 2022, where we're building a task-specific model on top of now what I have to call an old-fashioned transformer-based model using transfer learning and fine-tuning? Or should you try to do prompt engineering and use the zero-shot capability of these big LLMs? Now, this is where we're coming to the other part, the title of the talk, which is build versus buy. So I'll talk a little bit about what that means and why this is a dilemma that everyone faces, but in in the sort of industry side of the world to have the specific term of build versus buy. So build versus buy is essentially, are we going to take, let's say, raw resources and our own tools and know-how to build something, or should we just transform raw money right into the final thing? So this is the build versus buy, and this is so for if you're building software, if you have that capability in your organization, then there's always this question of, well, should we spend our time building this, or should we just go to some third party and see if we can buy that? I'll talk a little bit more in a second about that. It's not quite that straightforward, but that's basically the dilemma is, do it on your own or get it from somewhere else. A lot of the real reality is, I would say, is that it's usually more of a question of how much of each of these things are you going to do. Rarely is there a off-the-shelf product that does exactly what you need with no change to it. So here I just put in these pictures because there are these people that like to take, say, IKEA stuff and hack it. This one on the right is someone decided to use an IKEA desk as the case for their computer, which is either clever or horrible, depending on how you want to look at it. And then on top of that, there is no such thing as building from scratch these days. We're always building on top. I mean, the example of how you do stuff in 2022 when it's build is you take, you're downloading an open source thing that someone has already spent an incredible amount of effort training, and then you're going to do the fine tuning. So it's important to keep that in mind, just to humble ourselves, of course, but still, we're always building on something else. So I'll talk a little bit about the pros and cons here. So maybe I'll say one thing I didn't put explicitly in the slides is that buying could be getting something for free, but the main thing is you're pulling in some third party thing and using it versus building something that is specifically for what you need. Some of the pros and cons of building are the pros for doing this kind of, let's say, 2022 style NLP is that it's a well understood process. People have been doing this for a while. You can look up how to do it. You may have done it yourself many times. Typically, you'll end up with more reliable and more deterministic results. There are some details you can argue about that, but I'd say that's probably generally the case. You can also build probably a more understandable modular design because you are taking the pieces and putting them in ways that you need them. And you can typically, for these types of things, you're doing something very narrow. You already have the infrastructure for doing this because that's the way you've already been doing it. And you're already using a lot of the tools you already know. And as of today, it seems that for a lot of the benchmarks for these types of tasks, that there are supervised systems that are still beating these zero shot systems. So the thing about the zero shot is that a lot of them are very good at doing this, doing lots of these different tasks. But on the other hand, a dedicated supervised a system that's been trained with supervised learning in the end or fine-tuned are still able to beat that. Now I added this asterisk there, which is that things are changing very rapidly. So maybe by the time I give this talk today, this isn't true. Certainly not for everything, but it's possible. Some of the cons are that because you're doing supervised fine-tuning, you may need what's relatively a lot of data, and which is exactly the opposite of when you first learn about fine-tuning and transfer learning, is that you're learning, oh, this is a way to get around having to use a lot of data, but it's all relative. In this case, the pre-trained models that you're building on top of may have used an incredible amount of data, but still for doing this kind of fine-tuning, supervised fine-tuning, you might still need enough data that it's painful to get. It might be either expensive, say if you're doing radiology and you need to hire a bunch of very expensive radiologists to give you expert labeling on things, or any kind of things where there's just a lot of manual process involved, or if you know just straight up have to buy the data because it's something that's not available in a public way. Um, it may take longer to get off the ground just because you have to do all these things first, which is mostly the fine-tuned training and all these other things. You're and the way that these are typically done is you're more likely to be responsible for the actual infrastructure that you're using. And then, you know, maybe there's one that's this is not as exciting to say we're doing this stuff. There are people are still doing sort of old fashioned NLP these days when it makes sense. And those are techniques that are have been used for much longer that are not using neural networks and all of these things. There are still use cases for that. But in 2022, that would not be as exciting as using transformers and fine tuning. But maybe now using transformers and fine tuning is not as exciting. Buying, using these large language models. So some of the pros there are that potentially you need much less training data. As we talked about before, you might be able to put in the prompt context, you know, a few examples, and then it does really well. You may be able to just call an API. If you're using a third-party hosted solution, such as OpenAI, OpenAI's models, you know, maybe the main difficulty you're having there is just call the API versus doing a lot of other stuff. Potentially, also, you could use the same underlying LLM for many tasks. If you are using prompt engineering to get what you want, the only thing you're changing is the prompt. If you have a third-party service like OpenAI, it's possible also that the underlying LLM will improve while you're just sitting there because it's being developed by someone else. We'll talk about the flip side of that in a second. And also, you know, there's an aspect that this is the cool new thing. So people are, they want to use this because it sounds good. There's a lot of hype and maybe because it is cool. Some of the cons related to this are that a generative model, like these large language models, can potentially generate anything they want to. So even if you try to constrain what they're doing, they may decide that the most likely next thing in the sequence is something that is completely unrelated to what you're doing. This is very different than traditional kind of NLP, traditional machine learning. If you were looking at, let's say, sentiment classification, and we said we had negative, neutral, and positive, the model, because it's just outputting something in the raw state, the model could decide that, oh, it wants to put out some fourth class that doesn't even exist because it's just basically putting a word out as what's the answer. There are some ways to deal with this, but this is a potential problem, especially if you're trying to do something more open-ended where it can generate all sorts of stuff. And we won't go into sort of like many of the horror stories, but some of them are generating facts that don't exist. But I've seen it where I would say, hey, look at this document and return to me some of a sentence from this document that has something important, a sentence that talks about the warranty of this product. And then it comes back and it gives you the warranty. But then when you look, you realize that it just made it up. There was no warranty in the document. It's able to just generate something completely new. But in that case, without you going back and checking, you wouldn't know that it didn't get it from the document you gave it. It just was, it had seen a lot of documents, so it knew the kind of things that it should be saying. And overall, the model is just much more of a black box. You don't know what's going on. You don't know how exactly it was built. Several things like that. You can make some of these same criticisms for just using off-the-shelf neural networks of other kinds have been pre-trained, but in this case, it can be much worse, especially than if it's hosted by a third party that you're never really seeing the model itself. You're only interacting with it via an API. This is the flip side of one of the pros, and that's the model could change at any time. And in this case, we're assuming it's changing at any time for the worse. Whoever is hosting and owning this model, they may have been trying to improve it for some goal, and it turns out that improving it for that goal, which is unrelated to yours, actually makes its ability to do what you want to do worth. A lot of the stuff you have to do to deal with these large language models are essentially hacks. A lot of this whole idea of prompt engineering, it rubs some people really the wrong way, because there is not some deterministic input then to get some deterministic output. Rather, you're having to just keep playing around with the inputs to try to get the kind of output you want. And there are also things like dealing with context limits. So the amount of text you could put into one of these text LLMs is limited at this point. And so if you want to put in a document, for example, and summarize it, but it's longer than that context length limit, then you have to do something with that. There are several hacks that basically people have come up with. There's libraries to allow you to do some of the stuff now. But a lot of the stuff you have to do is basically hacks. If the model is generating something that is not what you want, a label that's not in your label set, you're looking for entities that don't actually, and the one they return doesn't actually exist in the document. You have to put guardrails in to try to handle those cases. If you self-host, the hardware requirements may be very substantial. That's also all relative. The stuff that people were doing 10 years ago, the hardware that people would have, certainly individuals have, they couldn't handle this at all. Certainly couldn't handle the training. But at the moment, when people are building these foundational models, the training is huge, but even the inference, running the models to produce predictions, can still be prohibitively expensive as far as the resources. Now, regardless of whether you do this build versus buy, which is using the 2022 NLP off-the-shelf stuff and fine-tuning, or if you do the power of LLMs, there are still a few things you need to do. One is you need to, every machine learning problem, you really need to start with a strong understanding of the problem you're trying to solve and the data related to it. And you also need a way to evaluate the results. I think one of the interesting things is that this has always been an issue with people coming into machine learning or working adjacent to machine learning that don't really understand how things need to be evaluated. But with the ChatGPT style LLMs, we're seeing a huge swath of people that have never done any of this before that are looking at it, and they may be starting to hack together solutions based on that without a strong understanding of how to do an assessment of what you might get out of that. So regardless of which approach you take, you're still going to need a high quality test set that you're going to use. And then finally, you're going to need lots of patience. Either approach, there is still a large set of empirical things you need to do just to get to the point where your model is doing what you want. So what do you do? Well, now that we're faced with this new world of these powerful LLMs, and we see this dilemma, how do we solve these quote traditional NLP tasks with these new choices? The way that I've been thinking about it is, one way to use these LLM-based systems is that they can serve as stopgap solutions. So I'm literally doing this at the moment. We are evaluating using LLMs to produce output for a model that we need to build, but we haven't had the time to build it yet. Another thing you can do is use those LLMs to bootstrap your training data. If you need to annotate a ton of data in, say, text or whatever, you may be able to essentially pass your annotation and labeling instructions to the LLM and then give it examples and have it do the annotation for you. I would say, and there's a whole discussion around how good of results can you get from less than perfect training data. This probably falls into that, although anyone who has done real world machine learning will know that your training data is almost never perfect for real world data sets of any size. That said, I do think for the test set, it's probably important that it be well manually reviewed so that you fully understand the quality and improve it as much as possible. And hopefully, tests would typically be much smaller than a training set you would have. I think Don't put anything in front of end users that comes directly out of an LLM unfiltered is probably a very good rule to follow. Like I said, these models can generate things kind of without bound, regardless of the instructions you give it. It may generate something that is totally different than what you were expecting. It could be as benign as a slightly different formatting or label, or it could be, producing something that you absolutely would not want your end users to see. So you need guardrails in place kind of at a minimum to do this. I didn't mention cost. I did mention resources somewhat, but I didn't really mention cost because I think that depending on exactly what you're doing, it may go either way. It may be that you need to spend so much time and resources on doing your fine tuning anyway, or even if you decide to go more from scratch than even fine tuning versus what you might be able to do with an LLM. So I would say that's sort of to be determined on a per project basis. That is actually it for the main talk. So I hope that you kind of understood that problem and you got some interest there. I have one more slide. I'll come back to this. And that is basically about, there's a lot of stuff that you can do with these LLMs, and a lot of the stuff people are talking about don't fall into this sort of handling traditional NLP tasks. But this is an issue. So, a lot of the stuff you've seen are people doing chatbots that are, actually chat well, code generation. There's lots of tools to help you code, like Copilot from GitHub there and several others. You can potentially review code. You can set up these agents which will take the output from one thing and then go do another thing, and then pass that output back to the LLM and do these kind of chained events and make decisions about what to do. Also, there's a big one is natural language interfaces to all sorts of stuff like databases, knowledge bases, and documents. There's multiple projects out there that are like chat with a PDF. Basically, you pass in a PDF and then you ask the LLM questions. I've done some stuff messing around with asking these models to generate SQL based on a natural language question, and then try to run that against a database. There's also a lot of issues there. But that's pretty much for my talk. And I would love to try to answer any questions. You can find me online. You can send me emails if you want it also later. My main website is roycoding.com. You can also see my books there at zefsguides.com, dshiring.com. But I'd be happy to answer any questions related to this or other general stuff that's maybe more about industry outside of like the medical research related world that a lot of this conference is, or a lot of this workshop is focused on.
Great. Thank you so much, Roy, for the great presentation. We'll start the Q&A session now. I'll invite our two mentors to feel free to open your camera or mic to monitor the chat or the session if you like, Diganta and Evaxi. So we can, as audience, if you have questions, you can go ahead and start asking in the chat. I'm gonna see, Marcia, thank you for your explanation on BERT, which is short for bidirectional encoder representation from transformers. Yeah, I'm really glad that you have touched upon these key concepts from NLP to zero shots and transformers. These are some of the concepts we'll touch upon in the future workshops in the next coming week as well. I see a raised hand. Please go ahead and unmute. Abdul Malik.
Thank you very much, Eugene. Thank you so much for the wonderful presentation. So my question is centered around a different industry use case for, say, chatbot, right? So say there is a particular business processing outsourcing company that, you have agents that receive calls and answer clients and stuff like that, and probably they've been doing it for a very, very long time. So there's a good, and usually those calls are usually recorded, right? So which means there's a pretty good chance that there's lots of data and something like that. How easy would it be, or what is kind of what would be the pipeline you would put in place to build a large language model around that is able to receive customer calls and answer based on questions and concerns, something like that.
I had a little difficulty hearing you, but I'll try to restate your question. I think the question was how feasible would it be to set up a system that would answer support questions, maybe?
Yes, exactly. Based on
Okay.
historical data of calls that have been received by those agents and how
So
they
I
answer.
think there are a few approaches to this. One that I would never recommend at this point is just allow people to talk to one of these models, just a sort of naked, if you will. Just let it just ask questions. Probably it doesn't know the answers that you need for your very specific thing, but also, like I said, because it can respond with anything possible, you may run into issues that you don't want. One of the ways that people are thinking about this is sort of like, how can you enable better answers based on specific knowledge that your company or whatever has? And this is sort of like the natural language interface to the knowledge base. And they mostly use a technique that's called, oh, I'm just forgetting the name. I think it's retrieval augmented generation. And basically what that is you would take, let's say you have a knowledge base full of documents. What you do is first you take each of those documents and you create an embedding, which is basically an encoding of the document, a rich, meaningful encoding. And then you'll take a question in natural language and you would also embed that with the same system. And then you would do a search. So like, let's say they said, how do I fix my refrigerator? And it would go and it would look in your database of help embeddings, knowledge. These are the documents you have, and it would look to try to find the documents that are most similar to that. Then it would retrieve that and put it into the prompt context. And your underlying thing would say something like, try to answer this question using these documents, the information in these documents. So then it would basically try to take that information and synthesize an answer to do stuff like that. Now, you're still kind of faced with the same problem of like, if the chat model can say whatever it wants. So oftentimes they're trying to put some pretty intense guardrails on those, where you would say, we think the answer is this, and it could be found in this document, where you would link to the document that you found, so that someone looking for help could get more help. Overall, I think the answer is these can certainly help out. Other ways people are using it is as assistance to the humans who are providing support, for example. So if you had, and I think this is a good use case, which is that you have the person who knows what the answer is supposed to be seeing what the output of the model is. So for example, if you had a support chat, and then you wanted to pass that chat off to another support person, the first person doing the support chat can then use one of these models, assuming it's built into your chat software, to ask for a summary of what's been the chat so far. What are the bullet points? And then that person, they just had that chat, so they know what's going on. They can see the summary real quick before they pass it on to another person. So there are several things like that can be done. A lot of possibilities. I don't know that you can just straight up automate. I'm sure people are trying to do that, but my impression is that probably would be a bad idea, just because there's so many gotchas.
Yeah, thank you so much. Thank you so much.
Hey Roy, can you hear me well?
Yes, I can hear you.
All right, perfect. Thanks for the splendid talk. We have a question from, I believe, Hamid. The question asks, Could you please elaborate a bit on the biasing impact on self-supervised learning? And maybe if I can expand to the question and add an auxiliary to it, if you could explain a bit into how biases permeate from the pre-training regime to downstream tasks when we, like, for example, call API of a model and we do not clearly understand the biases that are incorporated in the pre-training of the model. Thank you.
So this is always a problem with any kind of model that period is biased in the technical sense of, you know, how far are you away from what you're trying to do, based on, especially on your data. But there's also a second kind of bias that comes in, which is when you're trying to use a model trained for one thing to do something that was not the explicit thing that it was trained for in the beginning. And that can, I think at the end of the day, the answer is you need to have a very strong test set to evaluate what you're doing so that you can try to pick up on the biases. A lot of the stuff you'd hear about online are things that especially if you're opening up to sort of like all sorts of use cases, and there are many, you're trying to cover a huge set of things, different kinds of cases. So it might be hard to find all of those potential impacts of the biases. But I think it's definitely something you always have to keep in mind is the data that this was used to train for, is that actually aligned with the task that you're trying to perform? And if not, and it isn't going to be 100% aligned, how can we detect that? How can we mitigate that? I'm reading one in the chat now. So I think also from Hamid. In medicine, as you know, sometime in model building, we have constraints of less data, and with augmentation approach, we can increase the data, but it will impact on the accuracy of the model. Then how to increase the accuracy with other ways? Well, this is a very hard question, and it applies in all areas of machine learning. It's, if you don't have the data, what can you do? You don't have enough. I think one of the interesting potential things that these types of models offer, because they're huge models trained on a ton of stuff and they can potentially do some zero-shot things, is that you can also use them as part of an ensemble. I've never seen anyone really do this, but it's a possibility. So suddenly you've got a completely different model on completely different data, but you might be able to use it as an ensemble with the data that you do, a model that's trained on the data that you do have. I think, and there are other ones. I don't know if when you're talking about augmentation, I don't know. I don't even know how popular this approach is anymore, but there's another approach that's called test time augmentation. And the idea of test time augmentation is really about trying to modify the input as you send it to get a prediction. And then you kind of look at the distributions of what's coming out to try to get a consensus there. Really, though, I think, so the real answer is to get more real data, but the augmentation can definitely help. And then a lot of the difficulty in certain use cases is about whether your augmentations are doing what you want them to do. You typically see augmentation in computer vision where it's pretty straightforward. If you rotate something a little bit or slightly change the color or maybe add some blur, but you can tell generally, like, oh yes, that's still a dog in the picture, even though I moved it over a few pixels. But when you start doing that, especially on text and other things, it can be much less clear if you've been able to maintain the actual subject of the data once you've done the augmentation. I don't know if that helped or not.
Yeah, absolutely. And the Diganta also provided some of his understanding as well. We can continue asking questions. Oh, there it is. He also gave an example. But you mentioned previously that you have this really interesting short definitions on embeddings if you want to elaborate more on that as well. What on how it might be useful to,
So
yeah, go ahead.
sure. So one way to so embeddings are essentially a way to encode data that just makes it easier for whatever task you're trying to accomplish. And then, but one of the also nice things about data, about some embeddings, is that you can reuse them on other related tasks once you have learned how to learn the embeddings. Another way to think about it is just in any neural networks, you could almost think of all of the network up until the last layer is basically doing feature generation. You put stuff in there, and what it's doing is it's trying to take the input and put it into some abstract space that's much easier to deal with. So for example, if you're trying to do classification, the most of the network is trying to figure out how to put those inputs into some sort of linearly separable space so that the final classification is as easy as just doing sort of linear separation. When things are coming in, that can be, the raw data might be very difficult. If you've got just a picture of a cat versus a picture of a dog, like even if you ask a human to think of, like, write down the rules of how you would tell the difference, and even that's difficult. Like some dogs are smaller than cats. There's all sorts of weird things going on, and so it's not cleanly separable. But when the network is learning how to represent the data internally, it's trying to put things into different parts of this abstract space so that you can cleanly do a separation or whatever it is you're trying to do. Embeddings are essentially just the same as that. It's just that you might output the embedding at the end and then reuse it for something else. You could think of everything up in the network up until that last point as like creating the embedding, and then you're also training this last layer to do whatever it is you want. And that's exactly how embeddings are created. The sort of classic embedding example that people would learn about is a word to vec, which is basically how do you take a single word and put it in some vector space, that's the embedding space, that has some sort of meaning for what you're trying to do. And the way you typically do that is you just take a bunch of text, you look at each word, and you're trying to say something like, does this word belong in this sort of sentence? Or what you do is you take a sentence and then you like drop out one word and then you say what word should go in there. And you can do that with essentially the smallest network possible, and then you'll get these embeddings out of there. So I think at the end of the day, in my blog post, it basically says that the embeddings are, it is when you learn to transform the data so that it's more useful for what you want to do. There are clear limits to how useful it is. If you learned your word to vec in English and then you switched over and tried to do the same, you tried to run that same model, the embeddings, that's sort of the output is the transformation matrix. You ran that on Chinese, it would be meaningless because that's not what it was trained to do.
Mm-hmm. And for whatever downstream task, we have a lot of medical people here, but we have a lot of other different discipline as well. For various downstream tasks, how would you, let's say, fine tune the embeddings for it to be the most useful for your downstream task?
So I think if let's say you wanted to build a system that was going to try to diagnose a condition, and you wanted to input imaging and medical history and all these kinds of things. And so you could start off by taking, version 1 of this would be, I'll just dump the medical history into, say, BERT, and then I will just pass the images through, whatever computer vision model I've got on hand. and chop off the end of the model, what it was doing, classification, whatever, and get the output before it goes there at whatever kind of dimension that you wanted. And then you would pass those as features, basically just features, into some other model and see what happened. Now, there's kind of a question, and you can think about it, especially with neural networks, is that all you're doing is you are using some networks. The whole thing is a big network, and you can try to fine tune or whatever any part of that network. You could just say, okay, I'm going to use these as raw features and then train my small network that I've got at the end. Or you could unfreeze things and start going backwards and start, doing more fine tuning on those, assuming you've got a lot of data. So I think it's one of those ones that mostly you have to go in and just start messing around and see if you're able to get to the performance level that you feel is needed for your task. So I don't know that there may be some more general approaches to doing that, but I would say I think in the real world, mostly what people do is they just try a bunch of stuff. So you might try your basic BERT. You might find one that's BERT that's fine-tuned for medical stuff. Go get that one, because maybe it just works better at looking at these medical terms that other ones may not have seen, and they're throwing in a bunch of placeholders. You might do the same thing. Instead of just getting an off-the-shelf some sort of CV network, you might go for one that is more specific for CTs or MRI or X-rays or whatever it is you're doing, and just basically try those and retrain the way you're doing your fine tuning on the end part and see what that is. And then if that doesn't work, then you might try to start creeping back, and then you also might end up with a bigger problem where you need to get closer to training from scratch.
Yeah, no, absolutely. And I guess that leads to one of the other discussions we're going to have, which is doing this kind of research in industry versus in research. Obviously in research you aim to publish the new ideas and novel architectures. I'm curious what the objectives are, let's say, when you're developing this product, and when you're in this problem right now, looking into whether you want to buy or build yourself. What is the objective differences here? Are you aiming to push out products more than on more of a research perspective, or is it novelty on being different than other people and beat the other performances and so on? Or
So I think
what's best for your problem?
Right. I think in most industry settings, the answer is going to be that you're supposed to solve a specific problem, and you're supposed to get a solution as quickly as you can. And people don't care about novelty except for maybe the marketing department. And so it's very different than in academia. And I typically tell people, we want to do the most boring thing possible. I have to, try to tell that to my bosses that, yes, I know you want AI, et cetera, but probably we want to use AI as a last resort. And AI meaning machine learning. It's, if you can avoid it, don't do it. It's just so much more difficult overall to deal with than more basic stuff, more heuristics, whatever you're doing. Maybe you really do need machine learning, and that's one of the hard things, is to try to understand, do you really need this? So typically the way you go about it is establishing baselines and stuff. I think in academia, obviously there's a big push on novelty. And, in my time in academia and then kind of afterwards, I've seen the pattern of a new technique comes in, and let's basically try to redo everything with the new technique. And each one of those is a paper. And so, depending on how you're sort of doing the research game, if you will, that can be a very viable approach. I think back when I was doing medical physics and radiation dose estimation, there was definitely a group of people who their entire program was, let's redo what everyone has already done, but we're going to do it on GPUs to make it a lot faster. And they got very good at that, and they published an incredible amount of good stuff showing you what you could do. Back in my day of doing it, I was showing how you could do it on the cloud, because it was before people were really doing the cloud there. But the same thing, of course, is happening with machine learning. How can we do organ segmentation with the latest computer vision segmentation models, auto segmentation, which 10 years ago was still kind of a pipe dream, and now that's much more the reality. The question is, I do think introducing this cross-pollination of taking techniques that came from outside and putting them together, it's a great way to do stuff that can be new and publish. Sometimes I think some people don't like that as much because they feel like that's not as bold pushing forward things. But I think that just being more of an outsider now and seeing all these machine learning techniques come into all these medical areas, to me, I think it's just very exciting, because we just have these great new tools and we can do a lot of stuff that was much, much, much more difficult before. So it is, of course, in about finding the new thing that someone hasn't done, pushing the boundaries of the results a little bit more. If you're a student, I think one of the things you'll find is that it can be frustrating that you might have pushed something just a little bit, and that's about as much more you can do. But I think with, like I said, kind of the cross-pollinating coming, sometimes you can make the bigger jumps. I don't know if that's a good answer or not, but
Yeah, no, absolutely. Well, to me, what's the most exciting is to bridge something that's very obvious in another field to just use it, and then make something better in another field. This kind of identification of something obvious from another thing is
right. I think that's one of the keys, is that if you're also looking in other areas and have enough of a level of understanding, you'll start to see problems like, oh, this is a solved problem over here, but over here no one has yet made the connection that this is the same problem.
Yeah.
And that can be very fruitful. It may not be the same as coming up with a new law of physics or something, where it's like, here's a fundamental reworking and it's an improvement and whatever. It's a different level of satisfaction, but also that second one is much harder to do. So yeah, no. I don't know. I've always enjoyed bringing things together and synthesizing techniques and stuff.
Yeah, exactly. I sympathize with you. Let's take a look at the chat, and
I will say one last thing on that is that
go ahead.
I was recently looking at Google Scholar and saw that my highest cited paper was one that I wrote with one of my coworkers at a startup about machine learning. And I have, mixed feelings about that. On the one hand, it's nice to have citations. On the other hand, it's not about what I worked on when I was in academia, or my coworker, what he worked on when he did a PhD. So it's a little bit strange. On the other hand, machine learning has gotten so big now that, the biggest journals out there that aren't like Science and Nature, I think, are now machine learning journals. So probably our high number of citations is mostly just about the fact that there are more people doing this than there were ever doing, say, medical physics.
Yeah. Yeah, that's interesting. I think I'm also in middle of that journey during my PhD right now, so I'll probably have some more interesting insights in a couple of years. Let's see if there's more questions in the chat.
In
go
the
ahead.
meantime, while you're looking at the questions, I just wanted to ask and build up on some of the previous answers. I wanted to ask, how do you see the field change going forward, which is just large language models, but with respect to medicals and medical imaging, because these are private images. Usually they're not trained on large language models, and using APIs is not the most effective. So how do you see like medical imaging plus large language API going forward?
I think there are a few things. When I was doing medical physics stuff and that, 15 years ago, for example, I started doing stuff related to the cloud. And at the time, most people had never heard of it, but also people who did know, they were just like, no, that you can't do this in medicine. No one's ever going to do cloud stuff. And, there was a big shift. So it's still, and a lot of that came from, say, Amazon or whoever saying, hey, well, we've now got clouds that are compliant with the different regulations around doing this. So I think there will be, and in my company, just with like the ChatGPT stuff, they said, hey, we can't use this at all. No customer data is ever allowed to touch, ChatGPT, et cetera. But then not that long after that, OpenAI, they changed their terms of use. And they said, for example, if they have two different terms. One is if you go to the web and you use their ChatGPT interface. The other one is if you use the API. The API says by default, we will never use your data for training. We will never use it for this. So, and our lawyers reviewed that and they said, okay, it's Roy and his team are now allowed to use OpenAI APIs to do stuff with customer data because we feel that the assurances are there for security and IP related stuff. So it's slightly different concerns, but I think we'll see a pattern just like that where either, some of the big people who have those LLMs will come out and they'll say, this is a more secure space for doing medical related stuff in the different jurisdictions. I think on the more technical side that, the hope has always been getting closer and closer to needing very little data to do what you want. So I think the general thing with the computer vision models too, but what also the LLMs is that they get so strong at general tasks that your ability to fine tune them towards specific tasks with very specific needs will be much easier. And then another thing would be, I guess, with the LLMs, let's say medicine, would be that there is more and more progress towards self-hosting models like this. So when my company, for example, I've spent lots of time with our lawyers because of all these new things coming out and different concerns and IT security people, information security, and some of the questions were, well, could we just self-host these things? A lot of them probably wouldn't want to self-host, but I think there's a lot of people that are trying to get towards that. The same thing happened with the generative image models in the beginning. You had OpenAI and you had a couple other people that are making these announcements. We've got these new models. There was DALL-E 2 last year, but then there were researchers from some universities and they got money and they worked like with that company Stability.ai and they ended up putting stuff out public, open source, whatever. And then, people ran with that. That was the big one. There are similar things going on with the LLMs. And there are also people who will, they'll take some of the big public LLMs and they'll host them for you, or, NVIDIA or whoever else would be very happy to sell you the hardware to do this in a contained environment so that your concerns with like regulatory things are less so. So I think it's going to change the changing environment. It'll take a while, but I think it'll get to the point where this stuff is available for all these different use cases, regardless of the sort of needs that are, because of regulatory, legal, other ethical kind of compliance.
Mm-hmm. And how's the cost for that? If let's say that you're hosting something in your,
it really depends on. So there's a spectrum of things that are available now. There's if you go to Hugging Face has a leaderboard for open source large language models. And one of the things that you will see, if you see all the names, they always have a size there. So it'll be like 40B, 13B, 7B, and that means how many billions of parameters. but that mostly means that it's going to take more resources to actually run those. And we're just mostly talking about inference, but you can also do fine tuning and things like that. And there's a lot of work to get those to be smaller so that they're easier to run. But you basically will have a choice between how strong of a model you want and how cheap of a model you want, because as it is today, the size of the parameters and how much data they were trained on, well, the amount of data they train on doesn't affect, it's just the size of the parameters, but that will affect how expensive they are to run, basically. But you'll see that the ones, right now, I think is probably like Falcon 40B. It's an open source model that was it was released, and that one's probably the best one, but also it's going to be a lot slower than, say, a 7 billion parameter model that you could probably run on your home, on your laptop or desktop, if you use the very compacted version of those, the quantized versions. So I couldn't tell you numbers, but I mean, I can't run a 40 billion parameter model on my low end consumer GPU that I have on my desktop. Maybe you can run it in a couple of commercial grade ones, but those, you're looking at thousands of dollars to buy those. So it's it just depends on what your budget is. As a grad student, you may have to do a lot of begging to try to get your funder to get you those kind of things.
For sure. Have you ever, I guess, run into the problem of having too little data for whatever your model you want to build upon, and then so you don't actually need that large of a model to do whatever you need for the task at hand, and then it doesn't tune well?
I think it's still all relative. You might, you're often in the case where you need a large model and you don't have enough data. So that definitely happens. I mean, one way to look at it is to try to build a learning curve where you train with, let's say you've got 1,000 examples. You start off by looking at 100, train it with 100 examples, then train it with 200, train it with 300, and try to build a learning curve to kind of see what kind of improvement you're getting with more data. Well, this can be very noisy, but they may be able to give you the trend. If you're in this steep increase where you went from 100 examples to 1,000, you may be in this situation where more data really is going to help you. You may have hit a plateau, 500 at 500, and adding 500 more didn't help you. So that's kind of what you can often use as a guidepost to know where you are. As far as getting more data, there are sometimes situations where it's just impossible. I mean, if you looked at, data from Shakespeare, there's no more Shakespeare coming out. It's not like you can say, call up, someone who's been dead for hundreds of years and ask them to write more. If it's not enough for what you need, there are cases like that. Or if you wanted to analyze something about McMedhacks from 2021, it's done and over. There's no more data. So the best you can do is the best you can do. You may not even be able to train a big model because you just don't have enough data.
Yeah. Let's see. I think we don't have more questions from the chat. We have a lot of thank yous. So I just want to thank Roy again for the great presentation and all the Q&A period, and as well as our mentors for your answers and monitoring the chat. For our participants tomorrow, we'll come back and have our first workshop on self-supervision, which is very good that we had some primers today from Roy. So thank you so much, Roy, again, for your time and the great presentation today.
Thank you.
And yeah, so look forward to seeing you again some other time.
All right. Good luck, everybody. This is a great workshop. And thanks to the organizers for putting it on and having me.
Thank you. All right. See everyone tomorrow. Thanks, Roy.